doctorate was a project on cognitive radios, and then this was during my PhD, and ENCO2 was a project on basically cognitive radios again, but this was a Finnish national project, and this I did during my postdoc. And then after coming to India, I got this project from DST, Indian government, on cognitive radios for 5G. So currently I'm working on 3 IoT projects, pretty interesting and pretty ambitious. I will be talking about them towards the end of my presentation. So here is the outline of my presentation. So I will start with data transmission reduction in IoT network, which is basically a signal processing algorithms for IoT. And then I will talk about the machine learning for IoT, where I will be talking about occupancy estimation using machine learning. And both the topics are the works we have done in the, let's say, recent past, in last couple of years. Then I will be talking about as I mentioned in the previous slide, I will be talking about the interesting applications and projects of IoT which are running at IIIT Hyderabad. So quickly, let me tell you what is the definition of Internet of Things. So you search over the internet on the definition of IoT, you will get hundreds of definition with a lot of mumbo jumbo or jargons. To understand what is internet in simplest terms, we should look at the definition of internet which we use day in, day out, especially in the days of social media and even more during COVID-19. So what is internet? Internet is a network of computing devices such as computers, laptops, servers, tablets, and smartphones. Now, if we extend this definition to the things of daily use, we get our Internet of Things. Okay, so basically those things can be a bulb, it can be a iron, it can be a let's say a key, it can be a cycle, it can be a fan. Okay, so this is a very simple definition of Internet of Things. So you might ask how would you connect a thing to the internet? So that is by connecting an electronic chip consisting of basically sensors or actuators and microcontroller and communication module and a battery. Okay, so you have to embed this in a thing. So here the idea would be a sensor or actuator are monitoring or trying to actuate some physical phenomena related to the thing. And you need basically microcontroller for doing any kind of processing at the node, and then communication module connects the thing to the internet. Now these are just basic elements that I have highlighted. There might be other things as well, but keep in mind that there are millions of different kinds of things which you can put on internet. So this electronic device has to be low cost, low energy, and a result, it is also going to be low storage and low computing device. So this is how internet works. So you have sensors here which are monitoring some physical phenomenon, and basically it will send data to the gateway. This gateway is connected to the internet. On the internet, data will be stored somewhere and it can be analyzed somewhere. Based on the analysis, some command can be sent to the actuator so that a particular action can be taken. For example, if I have indoor as well as outdoor air pollution monitors, then I can keep track of, basically I can send this data, some analysis can be done. I can keep track of the, let's say, also the weather data. And if, let's say, the outdoor pollution levels are very low and indoor pollution levels are high, then you open the window so that the fresh air can come in. But on the other hand, if the outdoor air pollution is very high, then the better thing might be to keep the window shut and switch on the air filters. So then you will ask, why do we want to connect a thing to the internet? So by connecting a simple thing, right, like a speaker and mic here, it can become a smart speakers like Echo or Google Home, and it can have very interesting application with voice assistants such as Alexa and Google Assistants. Another application, interesting application can be a smart shoe. Now you will ask me, or you will wonder that what will you do by connecting your shoes to the internet? Now, applications of IoT can be amazing and are limited only by human imagination. Okay, so if you now put different sensors, including GPS, camera, etc., in a simple shoe, then a simple shoe can become a smart shoe, and that can help a blind person comfortably navigate streets in the city. Also, smart shoes for in general for everybody, we can use them to monitor our gait pattern, or gait in the sense of how the way we walk. And over time, if there is a change in the gait pattern, it may inform us of possible health issues with our leg even before they occur. So we already seen that for a thing to be smart, it did not have super storage or super computing powers. All it needs is a connection to a super storage or a supercomputer. And this thing I really find very fascinating. Now you would ask, why do you want to have an IoT? So obviously to add smartest to the simple things. And there are also several advantages of IoT. So it provides convenience and cost savings. So if you take an example of this beautiful smart thermostat called as Nest, which learns the behavior of the residents based on every time the temperature is set manually, like what are the temperatures people of the house like at what times of the day and which season. Now, based on the learnings, it knows how to optimally control the temperature of the house. Also, based on this, it it could increase or decrease the heating or cooling based on the number of people in the room, and it could switch off when no one is around. Also, you can control this remotely. Thus, it provides comfort, convenience, and cost benefits. Now, similarly for companies, if we let's say, connect different machines and processes of the company to the network, we will be able to do a real-time monitoring of the system using machine learning and AI-based algorithms. This will reduce human errors and it will increase the productivity. Also, this can help in predicting if the machine is going to fall even before it actually does. This way, we can take some measures such as so that the downtime of the machine or the company is reduced to the minimum. So let's assume that some machine is going to fail and you already know it. You can order some spare parts for that so that the downtime is minimized. See, what will happen if there's an issue with the machines is that either you need to then shut down let's say the process, which will result in a lot of economic loss, or let's say some faulty machine may also result in fatal accidents. So that way, IoT can help in basically improving the productivity as well as increasing the safety. So these are the top 10 applications of the many applications of IoT, like smart city. Then you have Industry 4.0, then have smart buildings. Then we have smart cars, the smart grid, then many, even health and many more. Note that the topmost application is a smart city, and smart city is a broad topic containing monitoring and management of critical city assets such as traffic, water, energy, waste, parking, etc. It is a very important topic, and for India, and you can understand that from the fact that India has already declared. India has a smart city mission which has declared already 100 smart cities. As such, we have established Center of Excellence on IoT for smart cities, and I will talk about it in the later slides. Already billions of devices are connected to the internet, and the number is only growing exponentially. And since many companies, the numbers of devices which are going to be basically connected to the internet are going to be in billions, tens of billions. It's a big market. Okay, and it's a multi-billion-dollar market, and everybody wants a buy of it. So you can see that all the big companies as well as the small companies are also part of it. One very interesting thing which you can also note here is that since IoT does not necessarily require a lot of infrastructure and let's say lot of funding to start a business. Just like in unlike the case of telecommunication, where the license itself is pretty expensive, and then you need standards, and the chain is not, the end-to-end chain is pretty complicated and very expensive, so only big companies can afford that. But if you see the IoT applications, one small application which I showed, the Nest one, a small company can afford to build it in a reasonable amount of time. So and keep in mind that the Nest was started, basically it was startup, and it was acquired by Google after a few years for billions of dollars. Okay, so this can so although it might look like we are only trying to address one small application, but that small application can have big benefits, as well as it can earn a lot of money. So there's a big scope for IoT applications in different domains. Even during the times of COVID, like everything has gone online, from health to education to work. In such scenarios, IoT can be of immense help. And I will quickly give two examples. One is from health industry, and then from the second from the manufacturing industry. In health, IoT can help with remote monitoring of COVID suspects and patients. It also helps in telemedicine, so that the consultation with the doctor can be done over a video call as much as possible. So basically, the remote monitoring as well as the telemedicine help to avoid saturating our primary services, which is very important right now. Then it's also helping the manufacturing sector, which has suffered a huge amount of loss because of the lockdown. And there the private priority is to get back on the track, and basically the idea is not to think much about the profit right now, but to sustain. Okay, so IoT can help there by reducing the manpower on the ground, by making the machines and processes monitored and operated remotely. So when I say this, what I mean is that it's not that I'm saying to reduce the workforce. What I'm saying is half of the people would be working from home and trying to remotely control some aspects of the, let's say, the production or manufacturing, and half of the people would be on ground. And recently, in one of the webinar, one of the IoT expert told that after basically during the COVID pandemic, a lot of Indian industry have adopted IoT in a big way. So then let me come to the that was more talk. I was talking more about the introduction to IoT. Now let me come to the signal processing aspect of signal processing for IoT applications. So the first topic is the data transmission reduction in IoT networks, and this work is in collaboration with my MS student who has already graduated. Then basically this work was done in 2018 and 2019. So Anish Shastri was my MS student then, and Vivek Jain was my third year BTech student. He was the honor student basically here. So IIIT Hyderabad has a unique culture for undergraduate research. So basically, the honor students generally work with a professor for 2 years during their basically third and fourth year, and continuously they work with a professor and try to do some undergraduate research. And generally, they are very, very productive. So one example I'm citing here is of the Vivek Jain. You will see that he's part of both the papers as well as the paper on the machine learning. Then this is also in collaboration with my colleagues or collaborators from LTU Sweden as well as NTNU Norway. So here's the motivation for the same. So many sensors are deployed in hazardous and inaccessible locations. So take an example, or one example can be forests. So recently, couple of months back, there was a huge fire in California. So let's say if you have deployed sensors there, right? So first thing is you can't power them through a continuous power source, in the sense you can't plug them to the mains, okay, because providing electricity at each location in forest might be very difficult. So most of them will be, the sensors will be battery powered, and then as I mentioned, they are almost like inaccessible locations. So it is very difficult to go and change the batteries for them. Second example I would want to give is, let's say we are currently doing this IoT deployment throughout the city. So if let's say, and the sensors, some of the sensors can be in smart cities, can be battery powered, and the number of sensors are growing. So let's say our house itself can have hundreds of sensors now. A building might have thousands, a block may have tens of thousands, and the city might have millions of sensors. And you don't want to end up changing battery of these sensors every other day. It will be too much of work, and too much of time. Basically, it will consume too much of your energy and time. So what we need is, we need to have basically, the sensor nodes have to have a good lifetime. So they need to have, we need to minimize the battery, what is it called, energy consumption or the power consumption of these sensors. So if you see the sensor node operations, the processes which consume energy are sensing, computation, and communication. So these are the three most energy consuming activities. There are others, but let's say these three are the most important or most power hungry kind of as compared to others. So even out of this, the communication is the one which is the highest energy consuming among, even among these three. So even if, let's say, if I sense a value, and if I compute something based on that, but if I feel that the value does not have any information, new information, for example, the value might not have changed at all in, let's say, last half an hour, 1 hour, then there's no point sending this value. So that way I can save a lot of energy, right? So what I'm doing is, even though I have spent some sensing and computation energy, but by not sending it, basically not sending the non-informative value, I'm saving on the communication energy, which is huge. Okay, so that is the basic idea behind this work. So what I'm trying to say is that what we will do is, we are trying to reduce the number of data transmission. Okay, and that has been termed as data reduction in this particular paper, just for convenience. So keep in mind that when I say data reduction, it does not mean that we are doing some kind of zipping or data compression. So we are just saying that we will not send data once in a while based on some criteria. So that is called, basically, the data transmission reduction is called as data reduction in this particular work. Just a minute. Okay, so this is the basic idea behind the work. What we are doing is, we are running basically at the sensor node and the sync node a prediction algorithm. Okay, so what we are trying to do is, based on the past values, we are trying to predict what is going to be the next value. If both sensor node and the sync node, let's say, are able to predict the next values properly, right? If they basically, if the sensor node predicts the next value properly, then it knows that the sync node is also going to predict it properly or correct. So then in that case, I don't need to send it, because sync node already knows the correct value or very close to the true value. So that this is the idea behind this prediction based data reduction, that you will run a prediction filter at sensor node and sync node. So you will estimate the next value based on the past values, and then you measure the next value at the sync node, sensor node. And if the estimated and the measured values are very, very close, okay, so the error, basically the absolute error, is less than the threshold for the given application, then I don't need to send that value to the sync node, because sync node also has made the estimate very, very close. But if the error value is very large, then we basically update the parameters of the filter, and we do send the data to the sync node. Okay, so these are the contributions of our work. So what we have done is we have custom designed low cost and low power sensor node using the commercially available hardware. Then we have implemented least mean square based and Sheva test based data reduction algorithm. So these are two signal processing algorithms which we have used on the custom designed sensor node. Now on the actual hardware, we have implemented the algorithm. In addition to the data reduction scheme, we have also proposed piggybacking and interpolation with the Sheva test-based data reduction algorithm. And then we have demonstrated the performance of the proposed implementation by parameters such as savings in the number of transmissions and current consumption and battery lifetime. Okay, so first what we are going to do is we are going to show how it reduces the number of transmissions, right? And then how does it translate into increase in the battery lifetime? That is the basic idea. So this is a LMS or least mean squares based data reduction algorithm. So you have basically what you do is at the nth instant you are trying to estimate the next value based on the past value. So this bold x of n minus 1 is nothing but the past n samples, and then w is a weight vector which is basically again at the n minus 1 instant what are the weight values. So basically this is nothing but is a weighted sum of the past values. Okay, and so what we do is then first we estimate the next value x hat of n based on the last n samples and the weights, and then we calculate the error. We basically estimate, then measure the actual value, and then we calculate the error between the measured and the true value, and then we compare that with the error threshold. If the absolute value of the error is less than the error threshold, then we do not send any value. Okay, and your x basically we just we replace the next value to be x hat of n instead of x of n at both at the transmitter sorry at the both at the sink as well as the sensor. But if the error is basically the absolute error is more than the threshold, then you do send basically the value to the sink, and you also update your the data vector. Okay, so instead of x hat of n, you are putting x of n here, and you also update the weight vector such that it depends on the error, the previous data set, and the step size. So mu is a step size which basically controls the convergence of the algorithm. So Sheva based prediction is pretty simple. What it does is it just simply uses the previous value as a estimate for the next sample, and then you are just trying to again find the error, and again based on if the error is less than the threshold, you don't send anything. If the error is more, then you send that value. The good thing about this is that it does not have any basically any complexity because there's no weighted sum. It just take the whatever value the previous value it was, or either take the if the data is received, then you take the current value, or if data was not received, which means that my estimation was correct, then I just take the previous estimate. So good thing about this is there's no very less complexity, and there's no tunable parameter like mu or the step size. So convergence is not a big issue. So here I'm trying to show what is the motivation for piggybacking and interpolation. So what this plot shows is the red curve is basically the time series. So in this work, we are monitoring temperature data, or basically the time series we are monitoring is the temperature. So and this square basically white dot here is the data which was sent to the sink, the last data sent to the sink. Now when basically let's assume that it is 27.75, and then when the value becomes 27.8 and for here the error threshold is 0.5, so you can see that the difference is hardly 0.025. So in this case, which is less than 0.5, so I don't send anything. Similarly, all these values, nothing is being sent. till here. Okay, so here the value has gone to 27.25, which is 0.5 degrees less than this. So basically it has become more, the error is more than the threshold, and in this particular, again, this value is sent to the sink. Okay, so this sink, basically we are sending this, and then directly we are sending this value in a normal, let's say, when a normal scenario. And at the sink, you can see the time series is this. Okay, because at the sink, for Shewart, let's say I was always using the previous, let's say, value, right? So you can see that the estimate at the sink and the actual time series, there's a big difference. Okay, all keep in mind that always the error threshold, or the error is always less than 0.5, which is the tolerable limit. But you can see that the mean square, if I start calculating mean square error between them, uh, it will be high, because the time series slightly deviated. So the estimator at the sync node does not capture changes in the time series properly. That's the issue. Okay, so now if I do, basically if I send, let's say, a few more points, when I'm sending this square dot, I can also send few more values. Okay, piggybacking on this value. Okay, so I will be not sending this circles at this instances, but at this instance. Okay, so the transmission are only happening at the square points, but with this square I'm also sending some circles. Although they are delayed, it's okay, but what will happen is it will improve the time series at the sync node. So when I say piggybacking, it's like I was anyway going to send data. Okay, so for every data I'm sending header. Header will contain address, source address, destination address, the way, or control data, like how to interpret the data which has been sent. And now if I send with this data which I was sending, let's say one temperature value, if I also send few more temperature values, you can see that it does not necessarily increase the data by, like, say, if I send, let's say, instead of one value, if I send four values, it does not mean that I'm sending 400 times the previous the normal times. Okay, it's just that the number of packets, keep in mind the number of packets are same, number of data points are increasing, but because of the header, okay, the burden is very, very small. So basically what is happening in IoT is that the header size are generally very large. So in this particular case, the header size is 11 bytes. Temperature value, one temperature value is taking 2 bytes. So if I send four more values, then it will be like a, let's say, if I send three more, then it will be 19. Okay, so 2 for basically 11 plus 2 plus 6, so it will be 19. So not, you can see that it's not increasing that much. And then once I do interpolation, you can see that if I do linear interpolation, then you can see the interpolated values are very, very close to the actual time series. So this is the hardware implementation. So as I mentioned that we have actually implemented this in the hardware. So we initially started with Arduino Uno, and what happened is that although we were getting very good results, that we were able to save a lot of transmissions, but because of the sleeping current of Arduino Uno, there was hardly any gain in the battery lifetime. So that's the reason we had to do some tweaking. So what we did is we removed all the excess components from Arduino Uno as well as the XB. So we are only using Atmega, and then XB's communication module. This is a controller, and this is your sensor. And then we are using battery of 2800 mAh. So as I was mentioning that we actually are only using the Atmega 328P microcontroller of the Arduino Uno, and then we also removed a lot of components from the XB S2C of the Zigbee. And then also we did some low power. We are using low power modes, and just like instead of using external 16 megahertz clock, we are using 8 megahertz internal. And after doing some kind of tweaking, we were able to reduce the energy consumption to such extent that we could see significant increase in the battery lifetime. Right. And this was deployed in our lab. So basically, this is 10 meter by 5 meter lab. Don't go on the dimensions are not proper. So this is double this, but For sake of convenience, we have just plotted it. This is 10 meters and 5 meters. So this is our lab where a lot of students sit, almost like 15 to 20 students sit. And here what we did is we deployed basically two nodes very close to each other, and again two nodes in basically indoor and two nodes outdoor. So outdoor nodes are deployed on the ledge, basically just outside the window. So on the blue one, there is a signal processing algorithm running, like data reduction signal processing algorithm running. In the green one, there's no signal processing algorithm. So it is sending data every 30 seconds. Sensing interval is 30 seconds. So every 30 seconds, it is sending data to the sink. While the blue one is sending data once in a while because it's running this filter both at the node as well as at the sink. And we collected data for 4 days, which amounts to 11,000, almost 11,000 data points. And the threshold we had was, the error threshold was 0.5 degrees Celsius. Then the parameters for the least mean square was mu, basically indoor and outdoor. We found the optimum value of mu, and these are the optimal values of the step size. And then the filter tap length is 9. Basically using 9 previous values, we are trying to estimate the next value. Okay, so this is a convergence of LMS algorithm. So what we are seeing here is number of iterations versus error threshold, and as a function of 5, basically the number of taps. So you can see that as the number of taps increase, okay, so basically this is for 5, this is for 9 and 13, you can see the convergence is much faster. Second is that if I increase the error threshold, the convergence is much faster. So there are two basically parameters which can increase the convergence. But if I use, let's say, a higher length or tap, then what will happen is the complexity will increase, because it will be like a summation of 13 taps, and again the weight had to be updated every time the value is not there is a more error. Okay. Then these are the plots of data basically measured and transmitted to the sink for temperature. So this is the raw data. Basically the indoor data and outdoor data are the actual data, and this is the one which is sent by the sensor, which is sensing every 30 seconds and sending to the sink, irrespective of whether the value has changed or not. Then you can also see the basically indoor Sheward, outdoor Sheward, indoor LMS, outdoor LMS. And so you can see the red, as I mentioned, the red line is for indoor, and then the light blue is for outdoor. You can see the variation in the temperature. So this was collected in June. So the values were going from, let's say, the variation you can see is from 20, around 26 to maybe 30 to 33. And some days the values were going up till 38, right? So on the other hand, so outdoor data, there's a lot of variation, but the indoor, you can see that during the daytime students were working, and then they will switch on the AC, and the temperature will basically remain slightly constant, and when they go back home, there was fluctuation based on the whether it is night or day, and then again you can see the slightly constant values and all. Okay. So second observation you can make here is basically if I just zoom in to this part which is shown here, you can see the reduction in the data transmissions. Okay, so if I see the indoor data first, you can see that I am sending, let's say, the green dots, which are the indoor LMS, and the blue squares, which is the indoor Sheward. You can see that I'm not sending these values all the time. I'm sending very less frequently. Okay, so you can see the blue ones are very rare, and slightly there are green ones. And for outdoor also you can see the same thing. Basically the pink as well as the black triangles, you can see that they are very less as compared to the the actual data which was sent if you don't do any kind of data reduction algorithm. So these are the results. So keep in mind that we had 11,000 data points. So if I use signal processing algorithm like LMS, then for indoor scenario, I only transmit 408 data points in basically out of 11,000 points. And with Sheward, it's hardly 58, which is huge. Okay. So what is happening is that you are getting huge amount of saving, like 96% here and 99%. And even for, let's say, outdoor slightly more data points are sent because the variation is more. But still, this is huge because you are hardly sending 100, 200 values for 11,000 data points. Okay. So what this savings means is that you are sending data point, let's say 99% will mean that you are sending out of 100 values, you're only sending one value. Okay. And one more big thing is that you can see the MSE is very, very low. It's not that big. The mean square error is not that big. One more thing you can see is the Sheward is actually outperforming LMS in terms of the savings as well as the MSE. So for the, let's say, we did the current consumption analysis, sorry, when we did the piggybacking and interpolation, we only considered Sheward. So as I mentioned that using the piggybacked values, I can do interpolation and I can do different kind of interpolation. So I can do previous. So whatever is the previous value, I'm just keeping, and then I will switch, and again it will keep it constant like this. Okay. So and then I can also do cubic. You can see second degree polynomial, and this is a basically just linear, just joining lines between the 2 points. So these are the results for piggybacking and interpolation. So you can see that what we are plotting here is a mean square error and the number of piggyback points. So so if I do piggybacking, but I don't do any interpolation, so there's a reduction in the MSE, but very less because the error is reducing only at the points where I send the values. But if I do interpolation, you can see that there's a huge decrease, and as the number of piggyback points are increasing, there's a significant decrease in the MSE. So this plot is plotted in terms of relative decrease in MSE here. Okay, so you can see that as less as 4 piggy points, I can get 70 to 80% reduction in MSE, which is huge. So this was for indoor and outdoor. Also, you can see that for indoor, if I use 1 piggyback point or 4 piggyback point, I get 38% to 75% decrease in MSE, which is huge. And for outdoor, it's even more significant, even for 1 piggyback value. So it is pretty good. The results are pretty good. Okay. So as I mentioned, we have seen how we have basically how much improvement is there in terms of data transmission reduction. Now we want to see how it converts into battery lifetime extension. Okay, the next step. So if you now see what I'm trying to show here is the current consumption analysis, and this I am showing for LMS. We also did it for Sheward. So if you see what is happening here is that this plot, there will be basically every 30 seconds, it's a periodic processing which is happening, right? Every 30 seconds, the sensor will wake up, process and send that value and again go back to sleep. So there are 4 states. One is sleep, which is kind of shown here, but it's not 0. It's like 6.1 microampere. It's not 0. Okay. Although it looks 0 here, it's not 0. Then you have processing state when your microcontroller is awake, then but the radio is off, and then you have radio is on, slight processing, and then transmission. So transmission takes the huge amount of current. It's like almost 45 milliampere here, you can see, but it's on only for 10 milliseconds. Radio is on for 30 milliseconds, and the current consumption is 35 milliampere. And the processing is hardly 5 milliampere, but it's on for 130 milliseconds. But although sleep looks very small, okay, 6.1 microampere, but it is on for 29,830 milliseconds. And this makes all the difference. If this was 1 milliampere, you will not get any improvement in the battery lifetime. Okay. So although it might look very small, but because of its duration, it really dominates. So it has to be very, very like reduced as much as possible. Okay. So then again, here in this particular plot, I'm trying to show the current consumption analysis for piggybacking. So although the timelines might be same, I'm just showing them slightly shifted just for convenience. Okay. So they might, let's say in actual, they might start at a similar timings, but you can see clearly that the red, this processing time in for without piggybacking and the blue one, the red and blue one are same. Sorry, the blue one is slightly more because now you have 4 data values you are trying in addition to the one which you were sending anyway. Okay. And then even the radio, when radio is on, you can see the this time has extended slightly. You can it extend slightly. So what is happening is that the current consumption will be slightly more as compared to the normal, let's say if you don't use any piggybacking. Okay. So that you can see from here that the current for, let's say, the radio on part is 35 here, 31 here, uh, without piggybacking, with piggybacking, right? So and even for, let's say if I'm transmitting, then it's 120. Sorry, when it's processing, it has increased from 120 to 124 milliseconds. Uh, the current is 5. Yeah, this is the time duration, right? So duration has increased a bit. So what it means is that the lifetime will be slightly decreased. But the main thing here is that the lifetime is going to be decreased very small. Okay. Keep in mind that this has given huge improvement in the MSE. Okay, so here's the battery lifetime extension. So you calculate the average current, and based on the mAh for the capacity of the battery. So we have used 2800 mAh battery here. So we can find the expected number of days, battery in days. So here what we found is that the battery, if you use in general 2800 mAh, and every 30 seconds if you sense, then this will run for almost 3 years, 1500 days. But if you run this signal processing algorithm, then the lifetime will increase to 4000 days or 4500 days, almost 3 times increase in the battery lifetime, which is huge. And with piggybacking, you can see that like the number of days are decreasing from 4488 to 4430 to 4 also to 4316. Okay, so what it means is that the number of days are decreasing by, let's say, few 50 days here, and maybe almost 150 days here. But keep in mind that it is giving you huge amount of reduction in MSE. Okay, so the decrease in the lifetime is hardly 1 to 3%, but decrease in the MSE is almost 38 to 75% if you use piggybacking of 1 and 4. Okay, so I would prefer, if you have any questions for this part, the signal processing part here. Hello. So I will request participants, if they have any questions, I can take maybe few questions right now on this topic before I move to the machine learning part.
So participants can either raise their hand or put the question in the chat box, please. Sir, there is a question, sir.
I don't see in the chat.
Yes, sir. I just tell you, sir. Dear professor, have you used VLSI signal processing algorithm to reduce power?
No. So you have not done any kind of tweaking on the VLSI level because we are using off-the-shelf components. So no, you're not done. Definitely that can be the next step. But I'm not expert on that VLSI front. So,
sir, one more question, sir. Is LMS and Shivat are the algorithms that can be used, or some other algorithms can be used?
there are many algorithms like for signal processing and data reduction. You can use most of them, but LMS is one of the most popular in the literature. But Sheward is something which we have proposed to be used, and it's simple and very efficient. As you have seen that it beats LMS for most of the data cases. Okay. We have, like in the sense Anish in his thesis has already shown that most of the physical phenomenon Sheward will work very nicely as compared to LMS. Does that answer your question?
Prashant, sir?
Mr. Prashant. Thank
Yes,
you.
sir.
Are there any more questions or should I move ahead?
Sir, there are no more questions, sir. Participants, do you have any other questions?
Okay, we can always come back at the end also, no issues.
Sir, one more question is there, sir. How can cyber criminals use it for his own benefits?
Sorry, what? Cyber what?
How can cyber criminals use it for his own benefits?
I'm sorry, sir, but I have not understood the question. Like, this is regarding cyber security?
Ajay Kumar, sir, can you raise your hand? Sir, you can unmute, sir. Ajay Kumar, sir. And you can ask the question.
Yes, I want to ask how can cyber criminal use piggybacking way for committing a crime?
No, sir, this is not exactly like this piggybacking is not between, let's say, other entity. It's basically the same sender can piggyback and send values. So I'm not looking into any cyber issues or security issues in this particular work. Okay, so I'm saying the piggybacking is happening only between the sensor and the sync, which know each other. And I'm not considered that scenario that there is a malicious user. Is it fine, sir? So security in IoT itself is a big topic, but I'm not touching it right that in this particular work. Is it okay, sir?
Ajay, sir, is it okay, sir?
Yeah, okay, sir.
Okay then. Thank you.
Sir, one more question is there, sir. Sir, what software
Yes.
you have used to simulate the results?
So we have not simulated the result. That's what I'm saying. So these are actually implemented on the hardware. So XB, then at Mega and all, right? So I showed the hardware. So this has been actually implemented on the hardware. And the current consumption analysis, I showed you the softwares which were used or the hardware, like the instruments. Like this, basically the current consumption was measured by this, and then the timing was using the key site. Okay, maybe should we then move to the next topic? I will again come back and answer the questions. And I really appreciate the questions. Thank you very much. It shows that you guys are paying attention and you're understanding it. So thank you very much for your questions. So I will move now to the second topic.
Yes,
I will take any more questions if they are there at the end of the presentation.
Sure, sir. Sure, sir.
Okay, so this is the second topic. So machine learning based occupancy estimation using multivariate sensors. Again, this is with my dual degree student Adarsh Pal Singh, and again Vivek Jain, who was also part of the first work. And this is in collaboration with one more professor from Triple IT Hyderabad, Vishal Garg, who works in smart buildings, and then two professors from NTNU Norway. And this work was published in Globecom 2018. So the basic idea behind this work is to understand how many people are there in the room, and how does it help is that if you know what is the occupancy pattern in the room, then you can actually reduce the energy bills. So how do you do that? In the sense that if nobody is around, let's say the AC can be switched off, okay, lights can be switched off if nobody's around, and if somebody's around, then you want comfort, right? So basically you don't want to switch off AC even if it's too hot. So what we are trying to do here is that if we know how many people are there, we can balance between the comfort and the cost. Okay, comfort, convenience, and cost. So that is the reason what we want to do is we want to understand how many people are there in the room. Okay, not only we are trying to detect whether somebody is there or not, but how many people. Like we are also trying to estimate the number of people in the room. Now already there are existing approaches like camera. You can put a camera and then that will easily tell you how many people are there in the room. Or you can have, let's say, RFID, smart wearables, Wi-Fi. But all of them are very privacy invasive in the sense that you don't want to have camera everywhere in your house or office, right? It will be very uncomfortable. So some people may misuse it, and definitely you don't want it in let's say your houses and your bedrooms and everything, right? So uh, so uh, what we were looking at is can we use privacy, uh, can we avoid using privacy invasive techniques for estimating how many people are there. So and a lot of people have researched on the occupancy detection, not estimation. So in this work, what we have done is we have used sensors like temperature, light, sound, CO2, PIR, which do not tell anything personal information. Okay, it's hardly, maybe it will only tell you are there or not and where are you. Okay, it will not tell exactly who exactly is there and all. And so this is mostly for the occupancy estimation application. So this is the experimental setup. So what we have a small lab where there are 4 desks. Basically 4 to 5 students can sit here, and then basically PhD level students can sit here, and then on this desk we have put a sensor node. Each sensor node will contain temperature, light, sound sensors, and then here as by middle we have put a CO2 sensor, and then on the door, above door and above the window in the room, we have put 2 PIR sensors. And the way we are collecting data is that all these sensors are in slave mode and they are sending data to the master. And so you can see here that for slaves we have used Arduino Uno, and then to communicate with for communication between slave and master we are using a Zigbee. And then for master we are using BeagleBone Black. And these are the different sensors for light, sound, CO2, motion. Now the data was collected every 30 seconds from the sensors. Now temperature, light, and CO2 were sampled naturally at 30 seconds, but sound has to be sampled at a very high speed. So how do you do sampling at only 30 seconds? So what we did is that we kept sampling it, continuously sampling it, and then we only report the maximum peak-to-peak value in that particular 30-second interval. On the other hand, PIR has to be sensed every 2 point second, and then let's say this will give you around 10 to 12, let's assume 10 to 12 readings. And even if I get in that particular 30 seconds, even one, let's say single motion, then I will send 1, okay? But if it doesn't sense any motion, then it will send 0 for 30 seconds. Now, the timing information was absent in all the sensors. So what is happening is that the master keeps track of that and it appends the timing. Basically, it puts the timestamps on each packet coming from the slaves. Now this was data again was collected for 4 days, which are again more than 10,000 points. And you can see the data looked like this from different 7 separate text files. Then there were 15 sensory features. So each physical parameter was basically a feature. So you have 4 temperature, 4 light, 4 sound. So basically 12, and then 1 CO2 13, and 2 PIR. So 15. Okay, so 15 features. And then the raw data set had some missing values, time skews, and no ground truth. So you need to do some kind of planning for that. So basically, you do pre-processing for missing values and time skews, and we also did something for the ground truth. I will explain here. So if let's say a few seconds variation is there, then we are putting same timestamp for all of them so that we have common vector. And for even let's say for a even one value of out of the 15 values for a given timestamp is missing, then we will simply delete that particular vector. And the ground truth we were maintaining by keeping a logbook. Basically, whenever somebody enters, he will write down when he entered and where he's sitting. And whenever he's basically coming out, he will also mark that I'm exiting. So we have a ground truth data also collected manually. So these are the features, and then these are only for we are shown for certain time of the observation data, not complete. So here this is the ground truth. So you can see that here nobody was there, and then 1 person, 2 person, and here some time there were 3 people. Okay. And you can see that there is an increase in the CO2 level as the number of people increase in the room. But you can see there's this slight, sorry, this is temperature, not CO2, this is temperature. So with increase in the number of people, temperature is increasing. So this data collection was done in the winter. Okay, so the fan was off and then the windows were basically shut. So in this given particular conditions, the temperature increases nicely with the number of occupants. And you can also see the light. Whenever people come, they will switch on the light in on the top of their desk. So you can also see slight jumps and all here. And whenever they go, the assumption was that they will switch off the light on their above their desk. Then sound is not showing any particular trend here, but it does detect. CO2 also you can see the increase and decrease with the increase and decrease in the number of people. But there's a huge lag. You can see that the person came here and the increase only is happening here, visible here. So to overcome that effect, we also tried CO2 slope, although it's not showing that much like a variation, but it gave excellent results. Okay, PI also you can't detect, like you can see that whenever people were there, you can see the increase in the value. PI value was 1, and whenever they were not there, it was 0. Then these are the different machine learning algorithms we have used. So one is the linear discriminant analysis and quadratic discriminant analysis, support vector machine, random forest. And so these are for understanding or estimating how many people are there, and unsupervised was used to understand how many principal components were there in data. Then this is the experimentation. We use tenfold cross-validation accuracy and macro F1 score were used. Then scikit-learn in Python was used. Normalized training data was used. And then the results were done in 3 phases. The first phase was the homogeneous fusion, in the sense that I will in the first phase I will only fuse data from similar sensors. So I will only fuse data from temperature only. Then I will take only data from light. Then I will only take data from, let's say, CO2. So heterogeneous fusion, you take data from different sensors. So basically, I can combine temperature and CO2. And the third one was only trying to see the dimensionality. So these are the results from the phase 1. Basically, so you can see the temperature only, light only, sound only, PIR only, CO2 slope, CO2 slope. CO2 slope is of CO2. So that's the reason I can combine both of them. And you can see that light is given the best performance with 97.3% accuracy, as well as 92.9 F1 score of 0.929, and then temperature also gives pretty is the second best. In the phase 2 results, what we did was we started by combining temperature and CO2 first, and then we added sound, then we added PIR, and then we added light. So in this particular fashion, we got results like with all the features, the accuracy was 0.984, pretty good, and then the F1 score was also very high, 0.94953. Without light, the accuracy is still good, but the F1 score is around 0.8. So these are the confusion matrix obtained in phase 2. So here basically the confusion matrices are needed because the data points are pretty skewed, and you can see here that the actual data points for 0 were much more than the out of the 10,000 points, 8,000 points were only actual 0, basically when nobody was around. And you can see that the case when only 3 people were there are hardly around 700. Okay, so that's the reason confusion matrix is important, and you can see that the out of actual zeros predicted were 8,117, and these were in error. Okay, so which you can see here that the error is reduced significantly when you also include light for the complete data set, and this is without light. Then the principal component analysis showed that let's say out of 15 features, let's say only 4 components have can give you 90%, 92% accuracy and 0.72 F1 score. So so the next I'm going to talk about maybe in another 10-15 minutes I will wrap up. I just want to now talk about the different works which are going on at IIIT Hyderabad related to IoT. So the first one is the IoT enabled smart cities, pollution, health and governance, and this project has been funded by Pernod Record India Foundation and DST Indian government, as well as the state government is helping us with this project. So this is a very multidisciplinary project. So I also have Professor Kavita Vemuri and Rajan Aftab from IIIT Hyderabad also working in this project. Kavita is from cognitive science background and is working on health. Rajan is from geospatial informatics. Aftab works on hardware, and Dr. Shailaja is from Public Health Foundation of India. Again, since health is one of the important topic in this particular project. So we all know that pollution is a big issue worldwide, and millions of people die every year because of pollution, and many more get seriously sick. So monitoring pollution is a very important topic, and in this particular project we are monitoring air pollution specifically. And if you see the current monitoring thing, so you can see that although they are very expensive, accurate, but they are very sparse. Okay, so the equipment might be in crores of rupees. So in Hyderabad you have 6 monitoring stations in an area of 650 kilometers square. So what happens is, because of that, at many places they are unavailable, in the sense that we live in this green box, some portion of the green box, and you can see that the pollution values are not available here. Okay, so most of the time the values are unavailable where we want to know the pollution values, in the sense that the places where we work, our homes, then the places where our kids go to school, and also the public common places like parks or malls and everything, right? So why I'm saying that not available, in the sense that the value which are, let's say, the pollution values which are, let's say, 1 kilometer away will not reflect what is the pollution at your place. Okay, so that is the reason. So what we are proposing is we want to have a very dense deployment of pollution sensor node in let's say a very small region, a small green square which I had shown you of around 4 kilometers square, and we want to deploy 50 nodes here. Okay, so keep in mind that Hyderabad has 6 for 650 kilometers square, and here I'm talking about putting 50 nodes in just in 4 kilometers square. Obviously, I can't afford crores of rupees, so I have to use low cost sensors. Okay, and the idea is that low cost sensor might not be too accurate, but let's say using AI ML based calibration models, as well as since you are doing a lot of sensors, maybe if you combine or fuse the data from different sensors, you will get pretty good indication of the values in your area instead of not having any idea whatsoever. Not only this, it will also give you street level pollution. Okay, so basically you can actually point to the source of pollution using this kind of approach. So what we will get with this thing is the map of different pollutant based on information processing, geospatial information processing, and with this we can also have real-time monitoring. So basically, the government can tell which cities are not attaining pollution levels, minimum pollution. Basically, if let's say the pollutions are going above certain values for most of the time for a particular city, then government can do some land use planning or traffic planning to reduce the pollution. And then basically it can do some preventive corrective actions, and then even to understand whether it is working, we need to monitor that, right? So last year we did this odd even plan in Delhi to reduce pollution, but is it working or not? Even to answer that question, we need to monitor pollution, right? So again, the localized early warning system. So we can maybe give, instead of banning or closing all the schools in the city, you can actually give localized warning that this region schools can be shut, but the other regions where the air levels are good, they can still keep the schools open. So these are the project objectives, and the basic idea is to monitor air pollution and the parameters like particulate matter, NO2, CO, CO2, SO2, NO2, as well as the weather data, because this also the weather also impacts the estimation or prediction of these values. And then the idea was to conduct, in addition to collect pollution data, we also wanted to collect health data through surveys, medical checkups, and from medical centers. And this data from these two sources will be then analyzed in the cloud, and out of that we will get a visualization platform where we can easily see the data in a very intuitive way. And second thing is we will get an idea of how what is the impact of pollution on the public health. This both the things can go to the governance, and when I say governance, it does not necessarily mean only government, but also the citizens. Okay, so basically citizens are also part of the governance process. So knowing what is the pollution levels actually will help citizens to raise awareness among themselves, and also to inform government about some issues which are occurring because of which the pollution is increasing. So that way everybody can contribute to reduce the air pollution everywhere. So this is the air pollution node which we have developed in-house, in the sense, but using off-the-shelf sensors. So we basically bought this SGA sensors and Node MCU and sensors and integrated them. And we had to use this kind of box because this is the IP65 box. Since we want to do outdoor deployment, and here the gas sensors will generally go, or in this particular case we are using temperature and humidity sensor inside this, so that it sees the actual temperature and humidity. But because if it's inside the box, then it might be slightly warm inside the box. So this is if this is in this kind of a weather shield with vents, then it will actually see the actual temperature and humidity in the environment. And let's say this is your SGS sensor and Node MCU, and then we had to use a battery. For battery backup, we are using power bank, and some places wherever we didn't had IIIT network, we used a GeoFi router. And a paper based on this had been presented in PIMRC London 2020. So this is the early results time series plot. So you can see that we deployed this last year and just before Diwali. So during Diwali, you can see that there's a huge peak in the values of PM 2.5. I'm not showing PM10. The results are similar. Then the value dropped in few days, and then after again it started increasing because of the onset of winter. So winter, because of thermal inversion, the values generally are very high everywhere. Okay, so you can see during winter the values are high, and then as the temperature started increasing, the values started dropping. But the drop was very significant around March because of the COVID-19 lockdown. Everything came to standstill, so no traffic pollution, nothing. So the values were very, very low. Then this is the dashboard we have come up with, and you can actually access this dashboard here, and you can see the live data every 30 seconds. You can see every 5 minutes we are updating, but every 30 seconds we are collecting. So you can see this, and we have started deploying it outside IIIT network now. So this has been deployed in Hillridge apartments, and there's one more we have deployed near Gachibowli flyover, and one in HCU. Then these are the results from the day of Diwali, and you can see that keep in mind that our campus is 66 acres, and we have deployed around 9 nodes. So this node was that day particular moment it was not working. So this plot is before firecrackers, and this is after. So there's a typo here. This is after firecrackers. So before firecrackers, I think yes, I think the day before it had rained, so the values were pretty low. And after firecrackers were bursted, you can see the hot spots. Okay, and here there are faculty quarters, and here there are hostels where the firecrackers activity had happened, and you can see the pretty the values increase from 13 to 360 and all. But keep in mind that although the values are very high in these locations, the values are very low in the other parts of the campus, just in 66 acres. Okay, so I'm saying 100-meter, 200-meter away, the values were very, very less. So the pollution can vary heavily from point to point, and that's what we have wanted to highlight. Okay, so this basically shows the variation in pollution level in a small campus of 66 acres. Next, I would again quickly talk about Center of Excellence. Another 5 minutes I will wrap up. So Center of Excellence on IoT for Smart Cities. So I am a coordinator for that, and there are again different faculty from, because it's a very interdisciplinary topic, and this has been established in January 2019 and supported by India-EU collaboration on ICT standardization, TSDSI and HC. TSDSI is the India standards body, telecommunication standards body, and HC is European telecommunication standards body. So the activities which are supported by the Center of Excellence are knowledge initiatives and research collaborations. On the knowledge initiatives, the idea is to conduct tutorial hackathons and workshops. We conducted several. We also have recently a MOOC on 1M2M. You can actually go through the MOOC and attend that. And we also had research collaborations. So 2 delegations from IIIT Hyderabad went to Europe. One went to Estonia in January 2019, and second went to France in July 2019. So I was part of the delegation which went in to France in July 2019, and that resulted in this very interesting proposal to MIT along with European Business Technology Center. So the visit in France resulted in this India Lab for Smart Cities, and this is a 7 crore project which has been funded by MIT. And faculty, all the faculty from Center of Excellence are involved in this, and this is in collaboration with European Business Technology Center, Smart City Mission, state and central governments, last CNRS, PwC, Amsterdam Arena. And you can see that the topics, the themes are related to water, health, waste, safety, energy, and specifically air pollution, building energy efficiency, water quality, quantity, smart classroom, street lights. And the objective is that objectives of this living lab is to do research on IoT for smart cities. Then basically IIIT Hyderabad is very famous for AI/ML kind of research. So we wanted to also collect a lot of our own data for this kind of research, and so that we can do research on the topics of AI/ML for smart cities. And then this the campus, the deployment in campus would serve as a test bed for smart city deployments. So what will happen is, let's say companies, especially the startups, which cannot afford to have this kind of testing facilities, will have a third party place where they can actually put their solutions. And this is like a small campus of people around 3,000 to 4,000 people in the campus. And so they will be able to deploy the solution in a living basically lab, in the sense which is not in their control, okay, not entirely in their control, but at a small scale. So if they are able to demonstrate their solutions in this, let's say, enterprise Hyderabad, then they can go to the government and show that, okay, the solution has worked, and then they can go for slightly more bigger deployment or testing or deployment directly in the smart cities. Obviously, the one of the important objectives is also to promote startups in the area of smart cities. So we also did this embedded system workshop. This is a second year course. Basically, CSC students in the third semester do this course, and generally we have 150 students in our CSC batch. So we had 50 teams of 3 students each. The idea was that the living lab, even before MIT approved the project, we were so interested that we started the first phase using this ESW course. Okay, and here the idea was that the hardware was institute provided hardware worth 10 lakh rupees, and again all these different topics were from the living lab, as I mentioned. So different aspects were involved in this. We did the students did okay. The focus of this particular course was mostly on the deployment, not on the lab part. In the sense, they already had these students have already done a course on Intro to IoT where they had a lab, so they had an idea about IoT, basically experiments and all. So here, but in the embedded system workshop, the idea was to actually deploy the solutions, build so applications, deploy them for a month, and then do analysis based on the data they collect. Okay, so that's the reason they had sensor interfacing, cloud integration, test deployment, then a soldering, and then again doing one-to-one integration, 3D modeling, first phase of deployment, again checking if the things are right, wrong, again doing second level of deployment. So I generally say this, that most of the experiments in college end up on the breadboard, but in this particular course, focus was that it started here, and then they went to zero PCB and actually designing a PCB as well as their 3D enclosures, especially if the deployment was indoors, and if it was outdoor, then you have to just simply use the IP65 boxes. So this is one of the team which deployed indoor air pollution in my home during their projects, and also some of them were deployed in messes. So this team also won a national level hackathon organized by this India EU project, and they were supposed to go to Germany for as a like a winning team, but that it couldn't happen because of the COVID. And again, this is outdoor deployment. You can see that this is in outside in balcony, my house balcony, and then this is at the main gate. This is one of the buildings. This is something unique about computer science students. Keep in mind that they are debugging the electronic circuits here. They are soldering. They are, which is, I think, this kind of activities generally CS students at least have not done this, and they were really happy about this. They faced a lot of issues, but then at the end they were very satisfied to do something which basically would be used in the, let's say, living lab. So you can see that they are doing the air pollution monitors, which already we have used in our research as well. So this is data analysis, the collection of data analysis, integration with 1M2M, also pushing this in Twitter and all. Thank you very much for your attention. If you have any questions, I would like to be very happy to answer them.
I request the participants, if any questions, so please raise your hand, else you put your question in the chat box. Sir, there was a question, sir. Sir, if any one sensor stop transmitting data due to technical glitch, how it can be identified and rectified to collect data in future?
Right. So what is happening is that we have the error feature. So in the sense error feature, this data is getting collected in ThingSpeak. So ThingSpeak can tell you if the data is not coming, or if the data is wrong, then it can send an email to us. So every day I get an email if some of the node is down, or even if some values are pretty wrong or something.
Sir, one more question is there, sir. What RTOS chosen for different applications?
Okay, so I don't have idea about. I'm not from the hardware part, so my colleague Aftab took care of that. But we have been using only Node MCU, so I don't think we have gone till the RTOS.
Sir, one more question is, dear sir, what are the security issues in healthcare and projects done till now?
Right. So very interesting thing that one of my colleague, not colleague, but one of my collaborators is Mr. Sachin Gaur. So he's a expert in security. So we are working with him to do a security audit of our network. Okay. So as I already mentioned, security in IoT is a big issue. So one example for healthcare. Let me talk about a couple of examples here. So healthcare, if you see, I'm wearing this kind of variables, right? But most of the time, actually, I can connect to these variables, collect data without you knowing, because it just simply allows you to do that. Okay. So most of the variables don't have any security feature like code or something. They don't share code or something. Some of them have, but not most of them. So that is one issue. Second issue, as I mentioned, is the you will not even think that it's an issue. So as I mentioned that we had deployed indoor air pollution in my house, and once we started looking at the data, it started giving privacy information. Okay, so it started telling what time of the day we were actually cooking. So the peaks were very clearly visible. And when we were cooking, let's say chapati, the peaks were slightly higher as compared to when we only cook rice. Because people can actually make out whether we are at home, and if you are at home, if you are not at home, if you are at home, then are we ordering from outside, or we are cooking at home, and what we are cooking. At least they get an idea, I'm saying. So this kind of issues are definitely there. How to test device integration and deployment. So you start with, let's say you start with the breadboard, see if everything is working fine, then do soldering and see if, again, everything is fine. So you need to do it in stages. Okay. So deployment is always very, very tricky. Many times you will see that you don't even have power plug where you want to deploy the thing. If you do that, then there's no Wi-Fi. Okay. So it's more like an iterative process. So device integration, I don't think it's a big issue, because the nodes we have hardly have few sensors. Does it answer the questions? Okay.
So there was one more question, sir. Sir, to go with IoT projects, should we have hardware knowledge?
Okay, so I'm not exactly from hardware background. I'm more like communication background. So mostly what is happening is that students are able to do all these projects very easily, because what is happening is, keep in mind what you should do is always try to use something, what is it called, public kind of a platforms. Don't try or open source platforms. Don't try to use very proprietary platforms from companies. Okay, even if they are giving it free, it's too much of a headache. Okay, so if you use something like Arduino, Node MCU, where a lot of code is already available, then it becomes very easy for students to integrate things and then focus on the experiment as compared to trying to debug all the issues which might be there in the, or develop some codes for, let's say, very sophisticated hardware, but then very limited. It's not, if it's not open source. You must have seen that a lot of companies would be very happy to give you kits, right? But let's say if they're not giving any support, those kits are useless. So be very, very careful when you try to do IoT projects. So try to mostly use something which is already open source.
So there is one more question, sir. IoT generated
Yes,
data
so IoT, right.
can be used for
Yes,
publication.
IoT generated data results can be used for publication. So there has to be some novelty in the sense that you can't just recreate the experiment done by somebody and then, but definitely very few people are doing it, and you have to be slightly patient in the sense that you need to collect huge amount of data. Okay, not like only I will run this for 1 hour, see what data is coming, and it is done. But you need to also do calibration. You need to also check whether the data is right or wrong, because sometimes the sensors might be very bad. Sometimes even good quality sensors will not be able to use unless and until you do some calibration. So you need to find if somebody has done this kind of work, and just like we did for our the data reduction algorithm, right? So there are data sets available already, but we wanted to use our own hardware. So we collected data. Then on top of that, we did some more work in the sense the analysis and the use of different new algorithms. So you need some novelty. You just simply can't generate data and publish. But I'm saying that a lot of people have not even explored many IoT applications. So basically, people have not put a lot of things on the internet yet. So you have very good chance of publishing papers on this. Yes, I think that's it. Please, let me know if that answers your question. Is it fine? Am I audible, sir?
Yes, sir, you are audible, sir.
Okay.
Thank you, Dr. Sachin Garu. Your presentation is well, and the participants.
Sir, there is one more question, sir.
Yeah,
for
sir. Is it
layer-wise
possible
protocol
to use
implementation, what idea can be used? For layer-wise protocol implementation, what idea can be used?
Okay, so layer-wise can be very tricky in the sense because as I mentioned that we are directly using things. So I don't. It might be what idea can be used. So can you give one example for the layer-wise protocol implementation you have in mind? Dr.
C.
Pandeshwaran. So meanwhile, please do type in between. But meanwhile, let me answer Mr. Prashad's question. So is it possible to use IIIT Hyderabad resources from other peoples for research? So what do you mean by exactly by this? So we will be giving data sets. So we will be making some of our data sets public. People can use and try out the, let's say, algorithms on this. If you want, you can also come and deploy your solutions here if you want. In some cases, I can also guide some of your students to deploy the solutions in, let's say, at least the way we have approached it. I can also guide your students to deploy in your college. Dr. C. Pandeshwaran, can you please? Are you able to hear me? Yeah, sir. Can you?
Actually,
yeah, go ahead.
we are using contiguous environment. But
Okay,
in
okay.
contiguous environment, the hardware support is very less. The hardware cost
Okay,
is
okay.
also very high. So if we are going for custom-made development boards, custom-made development boards, low-cost development boards,
Okay.
which
But what is the application you are using? What is the application you are using? What is your application?
power consumption reduction, various
But why do you
methods
need
of
Contiki OS
reducing
for
power.
that? Why do you need Contiki OS for that?
Yes, sir. Contiguous
I'm saying
layer-wise
what is the
implementation.
microcontroller? What is the microcontroller you are using?
TI boards, sir. TI MSP 430
Yeah, but that's what I'm
M5438.
saying. Do you really need that heavy boards? See, my suggestion would be use something like to monitor the power usage, just use something like Node MCU, get the data, process it at the server. That is the reason I was saying that the TI boards and everything, right? Like generally, if you don't have expertise, it can become very complicated. So instead of custom made, try to use open source like Node MCU or Arduino or BeagleBone, something like that. So something which is you will easily get the
For
codes and
Node
everything.
MCU, we are not having support in contiguous.
No, but why do you need Contiki OS? That's what I'm asking.
Because we worked for the past 4 years in that OS. So we are
Okay, okay,
comfortable
okay.
with Sky modes and we are
Okay.
comfortable with TI modes. But other
Okay.
modes support is not provided by the contiguous manual.
Okay, okay, okay. Okay, fine. But that's the reason I said that generally it's always good to go for open source because a lot of support is available online. Like you can get a lot of codes, hardware is there, everything is like very well planned. Like people are using, a lot of people are using, so they will put the code in GitHub and all. If you go very specialized like TI and all, it becomes very difficult sometimes. Unless I don't have that much expertise in the hardware part, so I can't comment too much. But at least try to keep it as simple as possible so that my students can easily do things on their own. So the codes are available. That's what I'm trying to say. Codes are easily available in most of the cases, and otherwise they can code themselves. They are very good at coding. Our students, this generation, I'm saying. My email ID wasn't it mentioned? It's mentioned on the first slide. It's just first name dot last name at triple-id@ac.in. It's also mentioned in my website. I can write it if you want. I don't think there are any more questions. Are there any more questions? Thank you, everybody. It was really nice to give this talk to such a knowledgeable audience, and I'm very glad to see so many participants and participants who are really active. I'm really thankful to all of you for this opportunity.
So thank you, Sachin sir, for sharing your valuable knowledge with all our participants. And thank you so much for taking your time to be with us and having your fellowship with us. Thank you, sir. Thank you so much.
Thank you very much.
So dear participants, now we'll be having the second session. Samurthy sir. Samurthy, sir.
Yes, sir. Sir, am I audible, sir?
Yes, sir, you are audible, sir.
Thanks. So, good evening, one and all. Hello, sir, Rashekar, sir.
Yes, sir, you are audible, sir.
I am start, sir. Can I
Yes,
start?
sir.
Okay, okay. So, I find immense pleasure in introducing our Professor Dr. M. Kamaraj Garu, presently working as an assistant professor and mentor, academic strengthening and advancement in Godlavaleru Engineering College, Godlavaleru. Dr. M. Kamaraj Garu has completed his PhD from JNTU Hyderabad in low power VLSI and embedded system design. He has completed his BE and ME in the field of electronics and communication engineering from Andhra University, Visakhapatnam. Teaching is his passion, and that's why it is joyous process to learn from him. And a total of 27 years in the field of teaching and as well as